Well, thank you very much. Thank you very much for the invitation. Yeah, it's great to be here. Thank you, Mike, for all his organising, and also to Regina King for helping organise this. So today I'm going to talk about flexible ADMM for big data applications. So this is joint work with my postdoc advisor, Daniel Robinson at Hopkins. So I'm mainly interested in design of algorithms, so the talk is mainly going to be about this ADMM algorithm, but it's motivated a little bit by some big data applications. So I will try to provide a little bit of motivation where are some of the applications where this algorithm might be useful. So just a very brief recap, big data. It's this, this buzzword that is being talked about all around the place. Our world is becoming digitized. So we have heaps of instances of big data all around us. We have things like Google, social networking, government databases, ebooks, library catalogues, telecommunications, smart grid, stock exchange information, medical monitoring, just a few of these things. And so this is kind of related to all of us in our personal lives and our work lives. I know that my students, I'm teaching a course at Hopkins at the moment, they're all accessing the textbook as an ebook online. They can use it when they're at home. They don't have to lug around something heavy. I've also given them a little project using some stock exchange information. You can go to Yahoo Finance now and you can get historical data for thousands of stocks, daily prices for the past 20 years. So we have all this digital information available to us at our fingertips. So there's lots of challenges that come along with that. Obviously, we know some of them. The good things are huge amounts of data are available to the public, and the hope is, I guess, governments, local governments, they're hoping that we can use this information to make better decisions about our personal lives. But also, we as researchers, we're thinking, okay, well, we've got this extra data. What can we do with it? Can we create better, more accurate models of the world around us? Will this help us with our understanding? So there's lots of new challenges that arise. I say mathematical challenges, but scientific, technological, engineering challenges that come up with big data. It's a big kind of umbrella term, but it provides some kind of motivation for what I'm going to talk about today. So here I've got some nice pictures. Here's a picture of the Large Hadron Collider. This idea that now we can see tiny, tiny particles. I guess we have valid scientific experimental knowledge of the Higgs boson particle now. This is this nice idea that we have a computer at our work, but we can go home and we can VPN into it. We have access to all this information wherever we are in the world. We get to access it. This is the Square Kilometre Array. It's an array of radio telescopes that's currently being built in the outback in Australia. It's kind of winding its way out to, I think, South America and even South Africa. And they're hoping to, I guess, collect more and more data from space, I don't know, to learn more about the universe, and ebooks. So these are kind of applications to give you this idea that big data, it affects us in our personal lives, but it also gives us more research scientific challenges. Big data means different things for different people, and for me in optimization, when I say big data, what I really mean is there are some really nice, large, convex optimization problems that arise. So different disciplines will think differently about what big data means to them, but for me it means I have some big convex optimization problem, I want to solve it. Here are some more pretty pictures to try and start everything off. Aircraft design, scheduling problems, you know, flights have to leave at certain times, they arrive in destinations at certain times, so all this kind of scheduling, timetabling of classes in universities, etc. Compressed sensing, so this idea of we want to reconstruct signals from data, but we don't want to collect too much data, we want to try and be able to reconstruct the signal from as little information as possible. This is compressed sensing. This is the Firth of Forth rail bridge in just in Edinburgh in Scotland, so that's where I did my previous PhD. This is truss topology design, so designing structures. We've got to do things like minimise weight, make sure that they can hold certain amounts of cars and things that go over them, build them properly. Machine learning types of problems come up, very large instances of convex optimization. Image reconstruction problems, so here we've got the Shep-Logan phantom. This is some MRI data, just a picture from the internet. These white lines correspond to data that has been collected. This is the image that you reconstruct if you use kind of traditional techniques based on this very small amount of collected data, and this is a kind of nice picture that you get if you use something like compressed sensing, things like support vector machines. So if we go to a bank and we want to get some loan, the bank collects information about us. What is our gender? What is our age? Do we have a job? How much do we earn? Where do we live? All this information about us, and they want to decide, are you going to be a good person or a bad person? Are you going to make your loan repayments on time or not? Support vector machines, this is a big convex optimization problem. Networking problems in biology, protein loop closure problems. So these are just some kinds of applications of big data. That's probably all I want to say about applications. I want to talk more about convex optimization. What does this mean for my research? Because there are all these nice applications that arise, but I'm really interested in algorithm design, so that regardless of, or so that I can have an algorithm that will be able to solve many of these different kinds of problem instances. So what are some of the challenges of big data? Some of the challenges are I might not have access to all of my data when I want to start running my algorithm. So the data might come to me in time over blocks. And we can think of this in terms of imaging. If we have some CT scanner, we take one kind of X-ray through the patient, then we rotate and we keep on collecting multiple bits of data, I guess, one after the other. So I might actually want an algorithm that can start processing my data even after just one camera angle of data has been collected. So I might want to start, I might have this incomplete arrive in blocks kind of structure. I might also have a lot of data, so much that I can't store it on one single computer. It might be distributed over a network. So I might have to access my data or work with it in pieces. So these are some of the challenges. And this really means that we have some kind of shift in algorithm design. So the algorithms that I might have been used to be my go-to algorithms, maybe they don't work so well anymore. Maybe they need to be adapted in some way to work in this new kind of context. So really, this is the main point. I want to have an algorithm that's going to take advantage of any structure that is available in my problem. Because I have so much data, I really need to be working on these structured problems as much as possible. So I might want an algorithm that works on blocks of data, so that it helps with these first two issues. I probably want an algorithm that has low memory requirements. I also might want an algorithm that has cheap updates. So these are some of the kinds of things I might want my algorithm to achieve. Cheap, work with blocks, don't cost too much in terms of memory. These are just kind of big picture ideas. Okay, so here's an outline of my talk. Those are some of the applications. Now I really want to talk about the algorithm. So this is the alternating direction method of multipliers. So this is a really common algorithm. It's been used in lots of different engineering applications, studied in mathematics, we use it a lot. I want to talk about this just, I guess, historically, what is the kind of generic standard thing that we've been working with, talk about a few applications and some previous work, and then I'll talk about my own research at Hopkins on this flexible ADMM algorithm. So I want to try and give a nice, accessible if possible, this is my hope, that the first part of the talk is quite accessible, so that even if you've never seen this algorithm before, hopefully you'll have some understanding of it. And then even just to motivate why we might want new versions of this traditional ADMM algorithm. I'm also going to talk about a hybrid variant. I'll describe this more later, and then give some numerical experiments. Okay, so we've talked a lot about applications. But really, for the rest of the talk, I'm going to be thinking about structured optimization problems. I want to be designing algorithms that solve some of these big data applications, but really I want to be solving classes of problems, not maybe specific instances, perhaps. So here is an optimization problem that the alternating direction method of multipliers can solve. So here we have some objective function. We have f1 of x1 plus f2 of x2. I want to minimize this objective, and I have some constraint. This is a linear constraint, a1 x1 plus a2 x2 equals b. So what you can see is that this optimization problem has a lot of structure. If I ignore this constraint, and if I just pretended the constraint wasn't there, you'd see that this is a really nice objective. It's actually separable. So this function f1 only depends on the block of variables x1. The function f2 only depends on the block of variables x2. If I didn't have my constraint, I could just minimize those functions independently to get my answer. Problem easy. But it's this constraint that links together the variables that makes it a little bit of a challenge to solve. Okay? And so what we want is an algorithm that's going to take advantage of the structure and work really well on these types of problems. So the alternating direction method of multipliers is an algorithm for doing this. It assumes that the functions f1 and f2 are convex. We have these variables x1 and x2. These are probably vector variables. And we have some data that's been given to us. These are matrices a1 and a2 and a right-hand side vector b. ADMM is an algorithm that goes all the way back to the 70s. Here are some of the people who worked on it. Gabay, Mercier, Glewinski, Morocco. There are many people that have worked on this at various stages, but it was developed in the mid-70s. However, it has become incredibly popular over the last few years, and that has a lot to do, I think, with this big data phenomenon. So this really, everybody is now talking about ADMM. You can't go anywhere without somebody saying, oh, have you heard about ADMM? I've done this kind of work on it. So it is incredibly popular. So let's talk about this ADMM algorithm. So this is just my optimization problem again. ADMM is based on minimizing the augmented Lagrangian. So how do we define our augmented Lagrangian? I have my primal variables x1 and x2. You don't have to know much about this, but with my primal problem, I have an associated dual problem, and I have a dual multiplier. All you need to know is that this x1 and x2 are variables, and y is a variable as well. These are all going to be variables in my algorithm. How I form the augmented Lagrangian, I take my objective function, I plug it in, and then what I do is I relax these constraints. So I multiply my multiplier by this a1 x1 plus a2 x2 minus b, and this would be the Lagrangian, and I add this 2 norm squared term to augment it. It depends on this parameter rho. So this is my augmented Lagrangian. The ADMM algorithm works by minimizing the augmented Lagrangian. So here is the idea. If we could find points x1 and x2 that satisfied our constraints, then this term would disappear, it would be 0. This term would disappear and be 0. And if I minimized my augmented Lagrangian and found a point that was feasible, and I've minimized the augmented Lagrangian, I've actually minimized and solved my original problem. Okay, so this augmented Lagrangian is kind of working as a surrogate for solving, if I can minimize this, which just relaxes the constraints, I've solved my original problem. So how does ADMM do this? It works on each of the 2 variables in turn. So we input, we initialize, and what ADMM does is it works on the primal variables, and then it works updating the dual variables. So I realize I'm going through this kind of gently, but then we're all on the same page. So what we do is we update our first variable x1 by minimizing the augmented Lagrangian. So I fix my x2, I fix my y, minimize the augmented Lagrangian just with respect to my first variable to get my update x1 at k plus 1. Now I use that information that I've collected from x plus at k plus 1, I plug it into my next problem, I use this information when I'm solving to find my variable x2. So I minimize the augmented Lagrangian with respect to x2 now to give me my new update x2 at k plus 1, and then I update my dual variables. This is just called steepest ascent on the dual multipliers. Why is this a good idea? Well, we've already talked about this a little bit in terms of if we're minimizing the augmented Lagrangian, and we find a point that minimises the augmented Lagrangian and satisfies our constraints, I've solved my original problem. But the reason we block up the problem, solve for x1, then solve for x2, has a lot to do with the structure of the augmented Lagrangian. If I minimise the augmented Lagrangian just with respect to x1, I don't have to worry about this function f2. It disappears from my problem. This is fixed, they disappear. I've only got this small inner product, and then I have to deal with this augmented term. So really, this is very nice because of the structure of my problem. I'm really taking advantage of the structure of my objective function. I'm only minimizing, when I'm solving for x1, I'm only involving the function f1. Then I use this information from my update x1 at k plus 1, feed it back into my new subproblem, and I get an update for x2, which again only involves my function f2. So this is a really nice algorithm. It really takes advantage of all the structure that's available in the problem. Okay. So it's a really nice algorithm. It's simple to kind of explain. What are some of the other things that make ADMM so popular? Okay, one of the things that's important to me is that there are very nice convergence guarantees. So I know if I say to somebody, you should use ADMM, I know that if the functions they're using are convex, this just means there is a solution to my original problem, like there is a feasible, something satisfies my constraints. This is all this is saying. Then ADMM converges. So I can give you this algorithm, I can say, this algorithm will solve the problem you want it to solve. There are convergence guarantees. What happens is I get feasibility. This feasibility tends to 0 as I run my algorithm, and I also get optimality. So my objective function goes towards the optimal value p star as I run my algorithm.
There's some condition on the rho for that.
There's some condition on
Rho.
Yes. There's conditions on rho. Rho has to be positive, and there's large different. Enough, right? Has to be large enough. So there are some conditions. This is a simplified version, but yes, there are some conditions on rho. There are also variants of this algorithm where you can adaptively change rho, etc. There are different versions of this, and I've really simplified everything here. But yeah, in general, choosing your rho correctly, making sure your functions are convex, assuming that you have a solution to your problem, you get these nice kind of properties.
And then converge plus?
So I think you have to make certain assumptions, but I believe if you assume that your objective functions are strongly convex and maybe differentiable, then you get linear convergence, I believe. Otherwise, sublinear convergence. I have to double check that.
If you let rho increase to infinity, step by step, I think you can get superlinear.
Yeah. Exactly. So yeah, there's this rho parameter. If you use this algorithm in practice, you'll find that choosing this rho can actually be quite tough, and choosing it correctly can lead to an algorithm that works much better. And you can choose a bad rho, and your algorithm doesn't work very well. So this rho parameter, it does have an important role to play in the algorithm. Okay. So it's popular because we have some kind of sense of convergence, convergence guarantees, and it's also popular because it's widely applicable. So I wanted to just, I know I've given you some pictures of these applications, but I've also given you an optimization problem. How do these problems fit this structure? So suppose we wanted to solve this minimum norm solution to a system of equations, have some matrix C, some right-hand side D. I want to solve this system, but I want to add some regularization. I want a small norm. This doesn't quite fit the structure that I've said before because this is an unconstrained problem, and both these two parts depend on the variable x. So what I can do is I can reformulate. I can make two copies of x, x1 and x2, and I can force a constraint. So what I can say is, okay, well suppose we put an x1 in this part of the function, put an x2 in this part of the function, then it looks like these two functions are decoupled, and I add some constraint. x1 has to equal x2. So now it fits my kind of problem structure from before. Okay, so here's just in terms of the generic formulation, f1 of x1, here we've got a function, two functions, each depend on a separate variable, and then you've got your constraints. So b is 0, a1 and a2 are the identity matrices.
Why is it such a good idea to do this beyond the formal description?
Ooh, that I don't want to say it's necessarily a good or a bad idea, but you can do it. And I think one of the nice things about it really depends on your specific problem. It depends how large your problem is. It depends on, does your matrix have any special structure, to be able to decide whether ADMM is the right choice or not. So I don't want to say this is necessarily what you should always do when you're given this original problem, but ADMM can be applied to this problem. So one of the nice things about ADMM is it is so widely applicable. If you have a problem, you've never seen it before, and you're like, oh, I don't know what to do, this is a technique, adding a couple of copies of the variables, adding a constraint. This is something that you can do, and you know that you'll get some kind of reliable answer. It's not necessarily the thing you should do, but it's something you can do. You can go through a similar thing for compressed sensing problems. So again, what you've got is some kind of objective there, compressed sensing, you wanting to find a signal that satisfies some equations that has a small 1 norm, so you've got sparsity, make your 2 copies, then you've got these 2 functions that are kind of, I guess, each depending on a separate variable. Okay, so here are these 2 applications. I just want to talk about...
F1 is not smooth, right?
That's true. So F2 is not smooth.
Convergence still holds.
It's still okay because we've only assumed convexity. Yeah. So its convergence still holds, but for things like saying linear convergence, you might not be able to do that because you lose your differentiability. So you might be just.
The differentiability key to speed of convergence.
Why is it key? I think it's just an. Pardon?
It wasn't an assumption.
It's not an assumption of convergence, but it does have an impact on the rate of convergence, so how fast you would expect the algorithm to converge. I don't know. I mean, it will just be some artifact of the proof, I imagine. But I couldn't say for sure. Okay, so I just wanted to talk about another big data application. So suppose I had the following kind of distributed optimization problem. It's a consensus optimization problem. So I want to minimize some function. The function, I have a whole bunch of functions fi. I have n of them, and they all depend on a variable x. Now, what we could do, and what I've kind of suggested based on the previous 2 slides, we make copies of x. We would make n copies of x. Then we would minimize this objective, each function fi depending on its own xi, and have some constraint saying xi has to equal xj. And I can write this constraint in a nice way as ax equals b, based on this kind of structured A, choosing b equals 0. So, what I've said before is that ADMM works on these 2 block problems. I obviously can write this objective as 2 blocks. I could have just made 2 copies, x1 and x2, grouped the functions into 2 separate pieces, applied my 2-block ADMM. But what I've said before with big data is we want to really take advantage of as much structure in the problem as we can. So wouldn't it be nice if we could talk about an ADMM method that didn't just work on 2 blocks, but maybe worked on n blocks? And this is what a lot of the motivation for the research on ADMM is at the moment, is can we come up with a new algorithm that will really take advantage of this n block structure, rather than us having to lose a lot by partitioning into 2 groups.
Why couldn't you have gone back to the original formulation and do the algorithm that you had before, where I fix n minus 1 variable, I iterate on 1 and then
yeah, so you can partition this problem so that it's written as the sum of 2 functions. You definitely can do that, and you can apply the traditional ADMM. You definitely can do that. And the question is, maybe there's something better we can do by taking advantage of all of the structure in the problem, because we're kind of ignoring some of the structure if we just partition into 2 groups. We're ignoring the fact that actually my objective function is the sum of n functions, not 2. So this is the idea. You certainly can group into 2 blocks and apply traditional ADMM, but maybe we can do something better. Yeah, okay. So this is the question. Can ADMM be extended to handle objectives made up of n components? I.e., can we use an alternating direction method of multipliers to solve a problem of the following form. Minimize an objective that's the sum of n functions subject to one constraint, one linear constraint. Can we do this? So this is a question that is now very, very popular, extremely popular. And this is why so many people are working on this at the moment. Recent work for n equals 3, counterexample. ADMM is not necessarily convergent when n is equal to 3. So if you've got a sum of 3 functions in your objective, just doing a naive change in your ADMM where you would minimize your first block, your second block, your third block, multiplier update, not guaranteed to converge. Okay? So black mark, can't do that, no. However, if 2 of the constraint matrices, so we've got this A1, A2 and A3 now, if 2 of those constraint matrices are orthogonal, then convergence is guaranteed. So now the game is, what are the conditions that we can kind of put on our problem to get some kind of convergence? Can we alter the algorithm in a small kind of way, or make some more assumptions so that we can get convergence of algorithm even when there are more than 2 blocks? So this is the reference for that first counterexample, and then there's another paper. If one of the functions out of the 3, so you've got 3 functions, if one of them is strongly convex, then convergence of the 3-block case is guaranteed. So the answer to our question is, in general, if we're just naively changing this ADMM method, no, we can't guarantee convergence. Actually, in practice, it still works very well, but we can't guarantee convergence. And this may or may not be important to people, but it would give me confidence if I had some kind of convergence guarantee. So the options we have now are we adapt the original algorithm or we put more assumptions on the problem. These are our...
You mean convergence, you mean both that the sequence of it converges and it converges to the right place.
Correct.
Which would have one without the other. Correct.
So you get feasibility and optimality. Yes. Okay, and then there's been some recent work on the generic n-block case. If you get, in some very obscure cases, some very specific instances, you can prove convergence of your algorithm. You can prove convergence of your algorithm when all of these functions fi are strongly convex. But I want to now, so the remainder of the talk is going to be about creating this new algorithm.
Particularly the one norm is not.
Exactly. So there are. I'm going to talk a little bit later about some specific applications and how you can kind of massage this problem into a formulation that the algorithm will still be able to solve. But strong convexity. And so I just wanted to talk briefly about one more algorithm, and this is really nice. This is the Jacobian ADMM. So for the standard ADMM, we're updating our variables in a Gauss-Seidel fashion, cyclically. So we're using information from x1, k plus 1 in our update for x2. But here we can just do everything in parallel. This is a Jacobi update, so you just update all of your primal blocks in parallel. So this is a really nice paper. Works for convex functions, for an objective function that is the sum of n blocks. What they do is they add some regularization and update their blocks in a parallel Jacobi fashion. So here is the algorithm written now. So we initialize some parameters, etc. And here what we're doing in parallel now, so this is different from the traditional ADMM, but this is in parallel, you're updating each of your blocks. So what you'll see if you just ignore this term, this is just the augmented Lagrangian. And then what happens is we add this regularization term. So what you have here is you also add on this difference between the xi that you're trying to find and the xi fixed at your previous iteration. You've got this matrix pi that has to satisfy some conditions. But this is really nice. Well, because it takes, I guess, advantage of the structure in your problem. So your objective function is a sum of n functions. You can now solve, so each of these problems is in a small dimensional space.
So why is it that localizing the red term, why is it such a good idea?
So it's good because it helps stabilize the iteration. It just seems to work really nicely in practice. And it's going to be really important in the algorithm I'm going to talk about for various reasons. I think think in this algorithm you can get away for some, I think all of these matrices have to be positive definite. But it just, I probably don't have a good answer, but it just seems to make the algorithm work really well. No, I do have a good answer. It can make the subproblems much easier to solve. Sorry, it can make the subproblems significantly easier to solve. And actually, I will show you this later in the numerical experiments. So it may not be clear, but you can choose this PI matrix in a special way, and your subproblem becomes very easy.
And the selection of row depends on the matrices PI?
The matrices PI depend on row. They depend on row, and they also depend on, I've added this extra gamma parameter down here. Well, I haven't. These guys have. And the algorithm that I'm going to talk about, it is between 0 and 2. So it's a relaxation kind of parameter. Yeah, so this is really nice. So this is the algorithm that we're going to want. I mean, this works really well, and the algorithm I'm going to show you works a lot like this. Okay, so we've got this problem. We've got some objective function that we're trying to minimize. It's the sum of n blocks. We've got this linear constraint. Unfortunately, I'm going to have to assume strong convexity too. This is something that's a little bit disappointing to me, but it seems to be the only way that I can guarantee convergence at the moment. So anybody who wants to have a go at trying to get rid of this assumption, people would be very interested in this. So again, this is the problem that we want to study. Okay, so we can rewrite this problem if we wanted to. All I really want to say here is that we've got this super variable x, and it's all of our blocks x1 to xn, and we've got this kind of super matrix A that's made up of all our component matrices. Okay, so I want to develop a new type of ADMM method. We want to have some kind of convergence guarantees. We want to, in some sense, keep true to the original method. But something that is really nice with that Jacobian method is this regularization. So I want to also incorporate some kind of regularization in the method, and it's going to be called flexible ADMM for reasons that will become clear soon. So here is the algorithm. What you're going to do is we're going to take all of our variables. For variables 1 to n, we're going to update them in a Gauss-Seidel fashion. So again, if we just forget about this term for a moment, this is the augmented Lagrangian. Previously, we fixed all the other variables that we weren't updating at iteration k, but because we're doing a Gauss-Seidel, we've already updated some of the variables, so they're fixed at k plus 1, and we haven't updated some of the variables, so they're fixed at k. And then we're also adding in this regularization term. We've got these matrices PI that are positive definite, and they're going to help me help making these subproblems easier. So this is kind of.
So in the previous sort of slide, I guess you switched to Gauss-Jacobi, and now you're back to.
Yes. So the previous work that has been done is Jacobi, and so we are still interested in doing Gauss-Seidel. So this is interesting research question. People want to know, can you do this in a Gauss-Seidel fashion? But the nice thing is we know we can do it really well in a Jacobi fashion. But can you get some kind of advantage? I mean, the intuitive idea is, can you get some kind of advantage by always taking advantage of the latest information, the most up-to-date information? So here with our Gauss-Seidel, we're always using this information from the previous updates.
The proof you've talked about before required Gauss-Jacobi.
Yes, required Jacobi. Yeah.
So you want to go back to Gauss-Seidel because it's more.
It's
should be more effective.
Correct. Yeah, that's exactly right. Yeah. So we want to go back to Gauss.
Label your components. Is there a particular choice that is more desirable than others?
My block structure, I just assume that there's some block structure that's given to me in the problem. It might be the case that you have an application where choosing specific structure works really well, and you should do that if you can.
So you're talking about the order, right? Yeah, right.
Oh, the order. Okay. Some people have looked at doing different orderings. Yes.
Does it make a big difference?
I don't believe so at this stage. If you're just updating the variables, you're just updating each of the variables in one go. No. I don't believe it makes a huge difference. It can make a big difference in different algorithms where you don't have to just do one pass of the data, but maybe multiple passes. But for this kind of method, you do one pass of the data, and to me it doesn't make a huge difference, I don't think.
So the result that you have says that regardless of how you do the labeling, you get the same result?
so long as you consistently update so you just assume some general block structure. Somehow the problem has been, the functions might depend on variables that have different sizes, whatever. But so long as you always use the same cyclic ordering, you get convergence.
So why is it necessary that you have to keep the same order?
I don't think it's necessary because I think there are people who have tried to change the ordering. Yeah. But yeah, for the proof, this is just something we assume. But it's an interesting question.
So iteration.
Iteration correction.
You're doing one at a time.
Yeah.
The ordering.
So
possibly learn something. Right, and decide based on what you learn, different order is better.
Yeah, that's true. That's true. So yeah, there are people that I think have looked at kind of doing orderings where you have some kind of covering. So you so long as you cover all of, you at least do an update to each of your n variables during each pass. Then I don't know. I'd have to find the papers to be sure I'm answering this correctly, but I believe people have looked at this. Okay. Oh, sorry.
So the difference between the previous slide and this slide is only the update fashion, where the previous slide is a block update and this one is a cyclic update.
Correct. Yeah.
Is it going to be the case that this actually yields a little bit better convergence? Because for me, the previous update is much more parallelizable, especially when n is extremely large, which a lot of applications have these days.
So it's a very good point. It's a very good point. And actually, so I'm about to talk about this hybrid method, and this is really where things will work well, where I'm going to do a mixture of Gauss-Seidel and parallel updates. So this is providing me with a generic framework, and I'm going to get a convergence proof of it, and then I'm going to show as a special case, by choosing these matrices carefully, I'm going to be able to do some parallel updates and some Gauss-Seidel updates. But in numerical experiments, you seem to get that your algorithm works better if you're doing these. But I'm going to show a hybrid method very soon, which is it's a very good question. Okay, so let's just say I've got some convergence guarantees. Basically, what you have to do is you have to get something called a contraction mapping. We got it under these kind of assumptions. You recover a solution to your original problem, which is what you wanted. So this is convergence. And if we make some more assumptions, if all of the functions have Lipschitz continuous gradients and your matrix has full row rank, then I can get a linear rate of convergence. So this is the hybrid approach. And so I can just, as we've seen, some of the pros are we're adding all this updated information at every iteration, so this is good. We hope this leads to at least I say fast convergence. I really mean this in a practical and not a technical kind of way here. So hopefully it leads to faster convergence, but it's inherently serial. Okay, this is not a good idea in big data. In big data, we want to be doing things in parallel. So what I want to do is find some kind of compromise or middle ground. We want to add. So this is the algorithm. It's going to add new information after several blocks have been updated in parallel. It's going to use a combination of parallel and cyclic updates. So this is my formalization, but let's not worry about it too much. I'll just describe in words how this algorithm is going to work. So suppose I've got a function that's the sum of 100 blocks. And I've got 10 processors available, 10 computing processors. So what I'm going to do is I'm going to split my data. I'm just going to partition it somehow into 10 blocks of 10 groups of 10 blocks. So I'm going to group blocks 1 to 10 together, 11 to 20, 21 to 30, etc. I'm going to group these together somehow. What I'm going to do is I'm going to take my first group and I'm going to send each one of those 1 to 10 blocks to processors 1 to 10. I'm going to update them in parallel. And then what I've got is I've got blocks 1 to 10 updated. So I've got some new information. So that when I send my blocks 11 to 20 to my 10 parallel processors, I'm going to use the information from blocks 1 to 10 in this update. Okay, so I'm doing this mix of making sure I'm using parallel computing, so I'm using all the processing power available to me, but I'm also increasing or using this updated information wherever possible. So this is how my algorithm is going to work. You have to do some formalization. All this is saying is I'm going to have these super blocks, these group blocks. They're made up of sub blocks. I'm going to group my functions together into groups. I'm going to group my matrices together. So I have to formally partition the data. That's all that's saying.
So you're saying that you would do that, you will not do that if the number of available processors is large enough to do the whole thing?
Yeah, so if you could do everything in parallel, then you're going to recover this, this kind of Jacobi method that has previously been described. Yeah, so for sure, there's a lot of good, if you've got enough processing power available to you, updating in parallel seems like it makes the most sense. But in general, for a lot of these problems, you really have a huge number of functions and not as many processes as functions, or if there's these sub-functions available to you. This is this is when this type of approach is going to work well. Okay, so I've said that I can do this. I've said that I can do this in words, but there's a few little technicalities that I have to get around. Why have I said just blindly that I can do this? Why can I just update all these blocks within a group in parallel? Because I've got these nasty terms that show interaction between the different blocks in my group. And so what I have to do is, and this is why I've added these regularization matrices in my method, we have to choose the regularization matrices carefully, and if I choose them carefully, I'm going to be able to cancel out these cross terms. So long as I make these matrices in some kind of nice fashion, I can get this hybrid approach. Okay, so this is what my matrices are going to look like. So in the original Gauss-Seidel case, we just have these P1, P2, all the way up to Pn. So this is a group regularization matrix. So I'm going to have several regularization matrices, and they're all going to have this same kind of structure. On the diagonal, I've got some matrices P1 to P whatever, the size of my group. And on the off diagonal, I've got these negative row times my cross terms. Okay? And so long as I use this type of structure for my regularization matrix, I'm going to actually cancel all the cross terms in my augmented Lagrangian for my group. I'm going to be able to update everything in blocks. You're also going to be probably saying, oh, this is a big matrix. But you don't have to form this explicitly. All you need is just these individual block regularization matrices. So I use this kind of in an implicit sense to cancel off terms in my augmented Lagrangian, but I don't use them in practice. I just use these blocks along the diagonal. So I'm no more expensive than the Jacobi method that I said was really good to begin with.
You want the matrix to be positive definite?
The matrix has to be positive definite. It has to be sufficiently positive definite. So there's restrictions on these matrices. They have to be symmetric and they have to be sufficiently positive definite. Sufficiently with respect to the full matrix, constraint matrix A. So you might have to take the norm of that matrix. So this could be, and then multiply by, say, an identity or something. So I'll give some examples of the regularization matrices too, but they do have to be sufficiently positive definite. Yeah. So you're not getting all this for free, unfortunately. Okay, so this is the hybrid method. This is just explaining formally what I told you in words. What we're going to do is I have some groups and I have blocks within a group. What I'm going to do is I'm going to take my first group, I'm going to update everything from that group in parallel. This update has really the same form as it's always had, so I'm not paying more than I would for my Jacobi or Gauss-Seidel version. I'm updating all these in parallel. I'm taking this information, I'm feeding it back when I update my next group that I'm updating in parallel. I've done a full pass of the data, then I update my multiplier. Okay, convergence is guaranteed. This is the nice thing about this method as well, doing it in a hybrid sense. For the fully serial case, all of my subfunctions needed to be strongly convex. Here, only one function per group needs to be strongly convex. And if I separate the data into just two groups and update the first group in parallel and then the second group in parallel, this works for convex functions. Okay. There's some other people who have also done this for the two-group case, but our method is more general because we require more general regularization matrices, and this helps. I'll show you this in just a moment. There's also a method that works on convex functions, but you require a correction step, which is involved in the whole dimensional space. So the nice thing about this approach that I've showed previously is you're always working with these small subproblems. So this last method needs a correction step.
Sorry, just a probably relevant question. So all of these updates are first order updates?
So you just have you have to exactly solve your subproblem. So you have your subproblem for each block, which has to be solved exactly, which is the case for the Jacobi version and all the other versions at the moment as well.
Intuitively, that should not be required.
Do you mean you could get away with inexact updates?
Yeah.
Very interesting research question. Intuitively, yep, you'd hope so.
Dropping your tolerance to 0 as the iteration proceeds.
Yep, exactly. So you'd have to. So you can do this for the two-block case. You're absolutely right. You can update. You can have inexact updates for your two-block case. They're not very practical, these updates. You just assume that the sum of your, I guess, tolerances or inexactness measures are kind of bounded in some sense. So
You said that the algorithm has been around, or at least the idea of the algorithm has been around since the mid-70s.
yeah, it has. Yeah.
Nobody has looked at these questions.
People have looked at these questions in the two-block case,
Right.
for sure.
What's the answer?
So the answer is yes. In the two-block case, you can get away with inexact updates. And so now that we've got this big data applications, we're saying, oh, okay, let's scale up this. Let's try and do things in the n-block case. And so it actually is significantly harder to get, as we have seen so far, and there's heaps of people looking at these problems. So far, to prove convergence of, I mean, we know that it will not converge. It is not guaranteed to converge if we just use the naive n-block ADMM algorithm, because we've seen a counterexample. So people are trying to now say, okay, well, what's the smallest change I can get away with?
What's the reason why it doesn't converge?
There's just a counterexample. So
I know, but what's the reason? I mean, if I were to look for a counterexample, I'm not going to go into the desert and hopefully. That's the idea.
So it kind of is. It hinges on this idea that I mentioned previously about choosing these regularization matrices carefully. You get some interaction between the two variables, the two blocks of variables, and so they said, okay, well, if these so you get something like x1 a1 transpose a2 x2. You've got this interaction in your problem, so you can't just convergence just breaks because of this. And they say, well, if A1 and A2 have orthogonal columns, then this term cancels and you get convergence. To be honest, I haven't looked closely at it. This is my first dabble into ADMM, but yeah, this is the idea behind their kind of counter argument and why this orthogonality thing is useful.
Do you have any experience in solving problems which are not differentiable, so that we can solve let's assume we can solve the problems use subproblems with subgradient descent, as opposed to gradient descent. They are not differentiable, so you use subgradient descent. In practice, how do you have experience of that? So
I'm not assuming that the functions are differentiable. How about? I think I'm running out of time, but what I can do is I can show this kind of experiment. Now, there's a little bit of a problem here. Obviously, this is a convex function, and I've said I can only deal with strongly convex functions. So the nice thing is I can pull on some work of Woetao Yin, who says, okay, if you take your objective function and add on some 2-norm squared term, so long as I choose my alpha carefully, the solution to this problem is the same as the solution to the first problem. So I'm going to take advantage of this because the second problem is strongly convex and I can actually solve this. So I've got some problem data. I'm only looking at very small problems for these kind of numerical experiments, but you can. Okay. So I'm only looking at very, very small problems just to give you to get an idea of these numerics. There are people like in the Jacobi paper H-ADMM where they consider much larger problem instances, and I guess the assumption is our algorithm kind of costs the same and it works in the same kind of way, so you hope that the numerical results will be similar. Okay, and then you have to choose your parameters carefully. But this is the kind of interesting, or I think this is the interesting part, and this is really why this regularization matrix is important. So if I have this previous problem, I break up my subfunctions. My subfunctions look like this. Okay, so here I have these two parts. These are both separable, so I can write the x1 norm as the sum of the absolute values of xi. I can write this 2 norm squared as the sum of, if the xi are blocks, then it's just the sum of the 2 norm squared of each of the blocks, totally separable. So I can write my subfunctions fi in this kind of form. All right, and then I get a subproblem that I want to solve for my jth block. So all it is as before. I have these two parts from the objective. I have some regularization term, and I've been a little bit tricky. I can group all my variables that are fixed in this xj update. I can put them into some vector vi. You can just work out this, it's fixed. So I have this kind of subproblem. And what happens is, and it's probably clearer with the previous numerical example because I can show you soon, but what happens is if you choose your regularization matrices to have this form, so some multiple tau, some number tau that depends on the norm of the matrix A, it depends on the row parameter, it depends on your strong convexity constant, but these are all computable quantities, minus this row AJ transpose AJ, it's actually going to allow my update to be solved via soft thresholding. So even though I've got this kind of complicated problem, and if I didn't have this regularization term, I couldn't use soft thresholding here. I'd have to use some kind of iterative algorithm that would solve this kind of problem. And then I'd be in this dangerous territory where we have this intuition that it should still be fine, but we don't have anything that says for sure it is. Whereas because I've got these regularization terms, I've got a closed form solution that is cheap to obtain. Soft thresholding. So I'll just go back. I had a previous experiment for minimizing the 2 norm squared with ax equals b. This is just to show you again, for some subproblems you might have to solve a linear system. This might be, it's still in a small dimensional space, but this might be a dense matrix. And by choosing your regularization matrix again carefully, with the minus row AJ transpose here, I can cancel out this term. So I've got a diagonal on my right-hand side, I've got just some vector on the left-hand side, and this update is extremely cheap because I've allowed regularization to be used. So regularization has really helped us. It makes the subproblems easier to solve, stabilizes the iterates, and it also allows me to use this hybrid strategy. So here, I know we're at the end. Just some results. You have to choose. So here's the hybrid algorithm, the flexible, fully Gauss-Seidel algorithm compared with the Jacobi algorithm. You have to somehow choose these tau values correctly according to some theory. If we just blindly choose these values according to theory, you're going to get a large amount of regularization for J-ADM and smaller for these two methods. So the algorithms perform better in terms of the number of epochs is just one full sweep of my data. So updating blocks 1 to n once. Here's something that's a little bit fairer because here we're saying, okay, might not work very well for these theoretical values of tau, but in practice we kind of do parameter tuning. If I put all the algorithms on a fair footing by choosing the same value of tau for each algorithm, then you still see some improvement with this kind of Gauss-Seidel approach. It's not huge, but the nice thing about these two algorithms is you can push down, you seem to be able to, in practice, push down tau down smaller, and the algorithm still converges. Even though this is outside of convergence theory territory, you can still get convergence, whereas the J-ADMM seems to diverge when tau is too small. Right, I know it's lunchtime. Oh, sorry.
H-ADMM does not seem to do much better than F-ADMM.
No, it does just a little, yeah, it doesn't do too much worse.
Top one, it does better.
Yeah, and this is the kind of magic about H-ADMM, and I mean, this hybrid one is the one that I would suggest people use in practice because it has this nice strategy of, using all your processing power available, but also using updated information. So it's this hybrid approach, and it just is just because of the way you have to define these tau j values, the tau j values get to be smaller with this hybrid approach, so you're regularizing less. In somehow your algorithm, because of this, your algorithm doesn't need as many updates.
We try to use the same 1.23 for the F.
Using tau equals 1.23. Well, I have tried to keep all the taus the same in this parameter tuning approach. So, but no, I haven't tried it on that exact value. But with this parameter tuning approach, each algorithm gets the same value of tau to kind of see how this works in practice. So I mean, really, this is the one that I'm always going to be suggesting people use because it's this nice balance between Gauss-Seidel and Jacobi, so it's practical. Okay, so we've introduced this new algorithm. We've also introduced this H-ADMM algorithm, which probably works better in this big data setting. We've got some convergence theory for these two algorithms. I didn't say that, but the H-ADMM algorithm is not actually a different algorithm. It is the F-ADMM algorithm with data grouped and special choice of regularization matrices. It is just a special case of F-ADMM. So I don't need a new convergence theory. I already have convergence theory for this. And we've got some numerical results. Okay, thank you. Thanks for Mike for the invitation. Thanks, guys.